everyone. I once again welcome you back to my YouTube channel. This is going to be my fourth lecture on electrostatics. In my previous lecture, lecture number 3, I have discussed problems on Coulomb's law as well as superposition principle. We will further continue discussing problems and applications on superposition principle in this video. So we will be taking a look at the application of superposition principle. And we will try to solve few problems which have been asked in your previous PU board examinations. Right. Let us take a look at the first question. In the first question, we are given a triangle ABC, an equilateral triangle ABC, such that at A there is a charge placed plus 3 nanocoulomb, and at B we have minus 3 nanocoulomb placed. And the question asks you to find the net electric field at point C. Net electric field at point C. The distances are 0.1 meter. The distances are 0.1 meter everywhere. So if this is 0.1 meter everywhere, because it's an equilateral triangle, and these angles are of course 60 degrees everywhere. Okay, let's take a look to how to solve this problem. The concepts involved are, as I've already said, is superposition principle. What does superposition principle state? Superposition principle tells us the net electric field at any point, if you're given a system of charges, is going to be the vector sum of electric fields produced by these individual charges. So to find electric field at C, this is the question that is being asked to us. To find electric field at C, we will apply superposition principle, and accordance with superposition principle, this will be equal to electric field produced by charge at A plus electric field produced by charge at B. So let's call this as equation 1. We also know the magnitude of electric field due to any point charge is given by Q by 4 pi epsilon naught R square. So this is equation 2. So these are the two basic formulas we'll be utilizing to solve this problem. Okay. So this is about the formulas. Now let's just write down what is given to us. Charge at QA is going to be 3 into 10 power minus 9 coulomb. Similarly, charge QB is also minus 3 into 10 to the power of minus 9 coulomb, and the distances are 0.1 meter everywhere. Now let us just find electric field magnitude produced by charge A. This is equal to also electric field produced by charge B. The magnitudes are same because the charges are same. It is 3 into 10 power minus 9 at A, and we have minus 3 into 10 power minus 9. Don't think about this negative sign because we are looking at the magnitude, and magnitude is always positive. So EA will be equal to EB because the distances are also same. So therefore, we may write this as equal to, we will use equation 2 to find the magnitudes. So 1 by 4 pi epsilon naught value is 9 into 10 power 9 multiplied with 3 into 10 to the power of minus 9 coulomb divided by 0.1. If you solve this, 0.1 whole square rather, 0.1 whole square. So this will give you 27 into 10 to the power of 2 Newton per coulomb. So this is the magnitude of electric field at point. This is the electric field produced by charges at A and charges at B. To find the net electric field at C, we've already said we'll have to add these electric fields vectorially. It's a vector sum, meaning that you will also have to take into considerations the directions of these electric fields. So to find the net electric field, we shall draw the free body diagram. We shall make a free body diagram. A free body diagram is made by taking a Cartesian coordinate axis, x-axis and y-axis. Now the point under consideration here is point C. Therefore, point C is conveniently chosen at the origin. And we will show the directions of electric fields at this particular point C due to charges at A and charges at B. Now, we know that electric field produced by positive charge will always be directed away from it. Right? The electric field due to a positive charge is always away from it. While the electric field produced by a negative charge will always be towards the charge. So the electric field is towards the charge. So in the light of this, we can draw the directions of electric field due to A and B. So clearly A is a positive charge, therefore the electric field will be away from the charge A. Similarly, electric field produced by B will be towards it because it's a negative charge. So therefore, let us show the directions of electric fields EA as well as EB in our free body diagram. So clearly, the direction of electric field EA is going to be along the fourth quadrant, isn't it? This is the direction of electric field due to A at point C. And similarly, the electric field produced by charge at B will be along the negative x-axis. See, this is along negative x-axis. If you were to hypothetically assume this as your origin, so one electric field EA is in this direction and the other electric field is in the opposite direction. So which I've shown it clearly here. So this is going to be electric field vector B. Now, once we have figured out the directions of electric fields, we'll also have to know the angle between the electric fields. This is important because we know that if any vectors P and Q are two vectors, and if you have to add them such that P plus Q is equal to R, the magnitude of R is given by root under P square plus Q square plus 2PQ cos theta. 2PQ cos theta, where theta is the angle between the vectors. Angle between the vectors. Now, so we'll have to find what this angle here is. So if you complete the triangle, we know that this angle at C is 60 degrees. So obviously this angle here also will be 60. But the main concern is to find this angle here, this angle. So if that is 60 degrees, this angle here is going to be 30 degrees and this angle is 90 degrees. So the whole thing here is just going to be 120 degrees. So we will utilize the formula R, this formula here, to find the net electric field by choosing theta is equal to 120 degrees. So therefore, E resultant at EC, that is EC, will be equal to root under EA square plus EB square plus 2EA EB cos theta. So this is the formula. So if you were to simplify this by substituting all the values, we find that the net electric field by taking theta is equal to 120 degrees. This is very important. If you took theta is equal to 120 degrees and you simplify this equation, we find that the magnitude at EC is going to be 27 into 10 to the power of 2 Newton per Coulomb. It's very important to notice that electric field is a vector quantity and you should not be adding it like a scalar quantity. So it's not EA plus EB is 27 plus 27, which is 54, but rather it is 27 into 10 to the power of 2 Newton per Coulomb. This is because the directions have been considered and electric field is a vector quantity and therefore directions are very important to be included in your calculations. Now, what about the direction? Once we have figured out the magnitude of this electric field, we can also find the direction of this particular resulting electric field at point C. Now we have, let me show one more diagram. So this is electric field EB and this is the electric field EA. So obviously the resultant is found by completing the parallelogram. So this is the resultant. Sorry about that. That's a parallelogram that's supposed to represent a parallelogram. Let me draw it properly. So this is our resultant vector in which the diagonal is going to represent the direction of electric field. or EC. So which is basically along which axis? This is along the third quadrant. This is along the third quadrant. So this is how one finds the direction of electric field by completing a parallelogram. I hope this question was clear to you. I can further give you one more illustration where I can change the magnitudes of electric fields and then find the direction of electric field similar to this problem. What I would do is, let's say at A, we again have plus 3 nanocoulomb. At, if this is A and if this is B and if this is plus 3 nanocoulomb once again. And the question asks you to find what is the electric field at point C. I'm not going to go into a detailed calculation of this, which I will leave it as an exercise to you. But however, I will show you the free body diagram. The free body diagram showing the directions of electric field at point C, and I will leave the calculations as an assignment for you. Okay, so the free body diagram, again, we'll have to make a XY coordinate system. XY coordinate system by taking point under consideration. Which is the point under consideration? Point under consideration is C at the origin. Now let us show the directions of electric field produced due to electric field due to A and electric field due to B. Now notice that in this case we have two positive charges. So therefore, the directions are going to be in this particular fashion. Due to A, it's going to be away from the charge. So therefore, this is in the positive x-axis. So we can write this as electric field due to A, which is along positive x-axis. Now electric field due to B is going to be away from it again because it is a positive charge. Therefore, this will be along which axis, which quadrant rather, it is going to be in the fourth quadrant. So this is electric field B, EB. Now, how do you find the direction angle between the vectors theta? Simple. Again, you complete the triangle, right? Now, theta, if this angle was 60 degrees, and clearly this angle is also equal to 60 degrees. So therefore, the magnitude of electric field now is going to be root under EA square plus EB square plus 2EA EB with cos 60. In the previous problem, we had cos 120. Now we are going to end up with cos 60. Let's repeat the same problem with two negative charges now and check what is going to happen. So let us say with two negative charges, let's say we have minus 3 nanocoulomb here again we have plus 3 nanocoulomb. No, rather negative itself. And we are asked to find what is the net electric field at point C. So once again, we can show the free body diagram by considering a coordinate frame, which is XY axis. And the point under consideration again is C. Now the directions of electric field now in this case are going to be towards the charge because at A and B we have two negative charges. So the electric field due to A will be directed towards the charge. So this is EA. So this kind of falls in which quadrant? It falls in the second quadrant. Now what about the direction of electric field produced by B? Again, because it's a negative charge, it is going to be again along the negative x-axis. So this is the direction of electric field along negative x-axis. Now what's the angle again? So theta again turns out to be 60 degrees. So you can again utilize the above formula and find the magnitude of electric field at point C. So the magnitude, as you can notice, is going to remain the same. So such type of problems have been asked multiple times in your board examinations, and it is very important for you to notice and to know how to draw the directions of electric field and add them vectorially. Okay then, moving on to next problem, we will take up a problem in which we are given a square and we are asked to find resultant electric field at one more point. In a square, we basically see, look, if you took a look in this triangle problem, we had two charges and we were supposed to find electric field at one of the corners. Now, in case of a square, we will be given three charges. So in case of a square, we will be given three charges and we'll be asked to find electric field at the fourth corner. This is the question that will be asked to you in the exam. So let us take a quick question and try to solve it. So let's consider a square ABCD. ABCD. At A, it is given to you charge is 4 microcoulomb plus 4 microcoulomb. At B, the charge given to us is 8 microcoulomb. And at C, we are given one more charge which is plus 4 microcoulomb. And at D, we are supposed to find net electric field. Find net electric field at point D for the given charge configuration. Okay, now the distances, let me take this for simplicity as 1 meter. 1 meter everywhere. And obviously, if this is 1 meter, we know that the distance from B to D is going to be root 2 meter because it's a square. It's just by applying Pythagoras theorem rather, you would be able to see that it is going to be root 2 meter. All right. To find net electric field at point D, we shall consider the solution. Similar to previous problem, we are going to use which principle? Of course, the superposition principle. We are going to use superposition principle. In accordance to superposition principle, to find net electric field at point D, we will have to add up electric fields produced by charges A and charges B, charge C, and add them vectorially. So let's call this as equation 1. And also the magnitude of electric field due to a point charge is given by Q by 4 pi epsilon naught R square. So this is equation 2. So now let's quickly find out the magnitudes of electric fields produced by charges A, charges B, charge B and charge C, and then let us add them vectorially. Okay. So obviously the electric field due to A and electric field due to C is going to remain the same because the distances are same here. This is same 1 meter. And charges magnitude is also same. This is also 4 microcoulomb and here also we have 4 microcoulomb. Therefore, so electric field at A magnitude will be equal to electric field at C, electric field produced by C. So this will be equal to 9 into 10 power 9 because 1 by 4 pi epsilon naught value is 9 into 10 power 9 multiplied with the charge. Charge is 4 into 10 power minus 6 divided by 1 square, which is going to give you 36 into 10 power minus 3, 10 power plus 3 rather, 10 power 3 Newton per coulomb. However, electric field produced by charge B is different because this is the 8 microcoulomb and the distance from B to D is root 2 meter. So therefore, electric field produced by charge at B will be equal to 9 into 10 power 9 multiplied with 8 into 10 power minus 6 divided by root 2 whole square, which is equal to again 36 into 10 power 3 Newton per coulomb. So let's call these as equations 3 and equation 4. Now to find the net electric field, we again have to make a free body diagram where we show the directions of electric fields produced by charges at A, charge at B and charge at C. So let us consider a rectangular Cartesian coordinate system once again. So this is your y-axis and that's your x-axis. The point under consideration here is D, which I will be choosing it as a origin. Now let's show the directions of electric fields produced by charge at A, B and C. Charge at A is a positive charge, therefore it is going to be away from it once again. So this is going to be along the negative y-axis. So this is electric field ED, which is along negative y-axis. Now one can find electric field due to C rather, which is along negative x-axis. So clearly this is along negative x-axis. So we should call that as electric field due to C. Now electric field produced by charge B is also away from it because it's a positive charge. So this will be again along the diagonal. So that will be in the third quadrant. So this is going to be the electric field produced by charge. Oh, I'm sorry. I should have written this as EA rather. This is EA, EC, and that's electric field produced by charge B. This is EB. So we have three vectors here. EB, EA and EC. So we can add two of the vectors first and then add it with the other vector. So what I would propose to do here is first I'm going to add EA and EB vectorially and then consider adding the resultant of EA and EC along with EB. Now notice that the angle between EA and EC, that is EA and EC, the angle is going to be theta is equal to 90 degrees, which means the net, that is, if I take this as ER, which is equal to EA plus EC, is also going to be along the same direction as that of EB, because they are bisecting at an angle of 90 degrees. Therefore, the resultant of these two vectors EA and EC is also going to be along the same direction of EB. So let's consider adding EA and EC first vectorially. So we know that the magnitude of electric field ER is given by root under EA square plus EC square plus 2EA EC cos 90. As we very well know that cos 90 is going to be 0, so this term just vanishes off. So if you were to simplify the values, so that is root under 36 into 10 power 3 the whole square plus 36 into 10 power 3 the whole square, we are going to get 72 root under 72 into 10 power 6, isn't it? So this is going to be 36 into 72 into 10 power 6. So which on simplifying, let me just check what the value is. This is going to give us about 5.091 into 10 to the power of 4 Newton per coulomb. So this is the value of net electric field ER, that is due to electric fields produced by EA and EC, which is 5.01 into 10 to the power of 4 Newton per coulomb. And what is the direction of this electric field? And this is going to be along BD, which is already shown to us here. So this is the direction of ER, which is along BD. Now we have electric fields ER and EB, which are along the same direction. So we can just add them as it is because the angle is just 0 degrees between them. So which on adding them directly, we will have 5.091 into 10 power 4 plus EB value is already determined. EB value is 36 into 10 power 3. 36 into 10 power 3, which I can write this as 3.6 into 10 to the power of 4, which on adding gives us 8.691 into 10 to the power of 4 Newton per coulomb, which is along the direction BD. So this is the net magnitude of the electric field at point D. Rather, I should not write it as ER. This is basically the magnitude of electric field at point D due to system of 3 charges. So it's very important to notice that whenever you are given a square, it's very important for you to first add 2 electric fields and then add the resultant of these 2 electric fields along with the other charge. So you can repeat this problem by changing the values. One such problem that I would like to give it to you as an assignment work is to repeat the same problem by considering, this is an assignment work. So take -4 microcoulomb and 8 microcoulomb and take here 4 microcoulomb and try to find the net electric field at point D, E net at D. So if this is A, B and C, I want you to find the net electric field at point D. Take the distances to be 1 meter. So one more problem that I would like to give it to you as an assignment work. The second problem would be where we have 4 charges now placed at the corners of a square. So let's take this as 2 nanocoulomb and this as 3 nanocoulomb and this one as 5 nanocoulomb and the other charge as 4 nanocoulomb, and the distances are, if the distances, let me take the distances to be √2 meters everywhere. I want you to find the net electric field at the intersection point of the diagonals at point O. Find E net at point O.